Welcome back, everyone. Now we're going to jump into some examples for geometric sequences, geometric series, the sum to infinity, and sigma sums. Let's look at the first example. So we are given the geometric series 5 over 8 plus 5 over 16 plus 5 over 32 plus going on is equal to k. We need to first determine the value of k if the series has 21 terms. Then we are going to determine the largest value of n for which Tn is greater than 5 over 8,192. Let's look at A. So we are given the actual geometric series. We want to determine the value of k if it has 21 terms. This means that n will be equal to 21 because I know that there are actually 21 terms involved in this entire sequence. I need to establish what A is and what R is so that I can work to solve for k. Luckily, I can see that A will be 5 over 8 because it is the first term. I then need to see what my common ratio is. So I need to know what has 5 over 8 been multiplied by to get 5 over 16. Similarly, I need to know what 5 over 16 was multiplied by to get 5 over 32. Hopefully, everyone will agree with me that I multiplied by a half because 5 over 8 times 1 over 2 is 5 over 16. So I have my A, I have my N, and I have my R. I just need to solve for k, and k is my Sn because this is what the sum is equal to. So I'm going to substitute in k for Sn, which will be equal to 5/8, open bracket 1 minus a half to the power of 21 because there are 21 terms, all over 1 minus a half. Wonderful, let's plug this all into our calculator. So I've got 5/8 over 1 minus a half. Sorry, the fraction didn't come there. A half to the power of 21 all over 1 minus a half. So k is equal to, if I round to the second decimal place, 1.25. Great, let's have a look at B. So I'm now asked to determine the largest value of n for which Tn is greater than 5 over 8,192. So I'm actually looking for the position of the term where it's going to be larger than 5 over 8,192. So I'm looking for where Tn is greater than this. I know that I can replace Tn for a geometric series with AR to the power of n minus 1. Luckily, I know what my A is. My A is 5 over 8. And my ratio, which we discussed on the previous slide, is a half. So I'm now going to solve this inequality. But to do that, I'm first going to have to get rid of the 5 over 8 because I'm working to isolate my n. So first, let's get our calculator. And I'm going to say 5 over 8,192 divided by 5 over 8 is equal to 1 over 124. So 1 over 1024. Luckily, if I am aware of how to use prime bases, I know that 1024 is 2 to the power of 10. So 1 over 1024 is the same thing as a half to the power of 10, which is wonderful because I like to be able to get the same bases in exponential equations because then I can drop them. But I have to remember that a half is the same thing as 2 to the power of negative 1. So it's going to be 2 to the power of negative 1 n minus 1 is greater than 2 to the power of negative 1 raised to the power of 10. So essentially my inequality will say negative n plus 1 is greater than negative 10 because I'm allowed to drop the like bases. Now solving for negative n plus 1 is greater than negative 10, I'm going to take my 1 over to the right hand side, so it will be negative n is greater than negative 11, but I have to divide by negative 1, so it's going to be when n is less than 11. So the largest value for n for which Tn is greater than 5 over 8192 would have to be 10 because 10 is 1 less than 11. So the 10th term will be the largest value of n for which Tn is greater than 5 over 8192. Great, let's move to the next example. So I'm determined, this is the same slide, moving on to the next example. We're now going to evaluate the sigma sum where we have 8 times a quarter to the power of n, but please note that we are starting the sum at n is equal to 3 and we are ending the sum at n is equal to 11. Just a reminder, for sigma sums, I actually have to have my a and my d, or in this case my r, because that allows me to substitute into the geometric series formula. So I need to find the first 3 terms of this sequence. Because the actual series or the sum starts at term 3 is my a. Because term 3 is my a, I need to actually know what the value of it is. So each time I'm going to substitute in n is equal to 3, n is equal to 4, and n is equal to 5 to find the first 3 terms of this particular sum. So if you plug these 3 into your calculator, you will get a half, then an eighth, then 1 over 32. Those are the first 3 terms of this particular sequence, which actually creates our series. Great, so now that we actually have a, we can determine r because I have the first 3 terms. I still need my n for the sigma portion of this sum. A reminder that to find the number of terms involved in this actual series, I take the top number of the sigma sum and I subtract the bottom number and then I add 1. So the number of terms involved in this pattern will be the top number, which is 11, minus the bottom number, which is 3, plus 1. So you'll see that n is equal to 9. So there are 9 terms involved in this sum. Cool, everybody. So hopefully at this point you can see that I can actually do the sigma calculation because I have my a, because I have my first 3 terms, I'm going to be able to confirm my common ratio. And because of the sigma itself, the top number and the bottom number allow me to actually confirm how many terms are involved in this sum. So now we're going to take all those pieces of information and we are going to put it into the geometric series formula. Let's go to the next slide. So we've established that the first 3 terms are a half, an eighth, 1 over 32. If you went on, you would see that 1 over 1 to 8 is the next term of the pattern. We've discussed that a is a half because this is the first term that's being involved in this actual series. The common ratio is a quarter because to get from a half to an eighth, I had to times by 1 over 4. To get from an eighth to 1 over 32, I had to multiply by 1 over 4. And because I used top minus bottom plus 1, I know that n is equal to 9. Because I have my a, as well as my r, as well as my n, I can substitute into Sn. So the sum of the first 9 terms will be equal to a half times 1 minus a quarter. This is going to be to the power of n because it's the first 9 terms, or there are 9 terms rather involved in this sum, all over 1 minus a quarter. So let's plug this all into my calculator. So we've got a half multiplied by 1 minus a quarter to the power of 9 over 1 minus a quarter. Let me just make sure that fraction comes in. So this sum is equal to 0.67 if I round to the second decimal place. Great, everybody. Let's move on to the next example. So we are given the figure ABCD, which is a square. The square PQRS is formed by joining the midpoints of the sides of the largest square ABCD. This process of forming smaller squares inside each square is continued to infinity. Let's stop right there. The second I see the word infinity, what type of series do you think this is going to be? Hopefully, sum to infinity is rolling around in your head. So the question itself has given us a clue that we need to know what the value of the areas of an infinite amount of squares would be. But let's go to the board so I can show you how to do it. So we know that AB is 8 centimeters, which means that this length is 8 centimeters, as well as the lengths of all of the other sides of this square. We know that the area would be 64 because 8 squared is 64. But in order for me to actually use the sum to infinity, I've got my A now, which is 64, but I still need my ratio. We need to find the area of the square within ABCD in order to establish my common ratio. How am I going to do this? If I know that this is 8, and we know that P, S, R, and Q are drawn from the midpoints of the sides of the square. So that means that AP would have to be 4 units, and AS would have to be 4 centimeters. Because it is a square, I know that the corners are at right angles to each other. So I can do Pythagoras to find the length of PS, and that will indicate the length of each side of PSRQ. So PS squared will be equal to 4 squared plus 4 squared because of Pythag, which means that PS squared will be equal to 32, which means that PS is equal to the square root of 32. So this side itself is the square root of 32, but if I'm finding the area of PSRQ, it's going to be 32 squared, or the square root of 32 squared, which means it's just going to be 32 centimeters itself. So because I now have the first term, the second term, if you were to find the area of the square within PQRS, you would see that it has an area of 16 centimeters squared. So I can actually see that I've got my pattern. So I can substitute in to the sum to infinity. My A is equal to 64. My ratio between each of these, hopefully everyone will agree with me, that I have times by a half. Because 32 is half of 64 and 16 is half of 32. You can also use your R is equal to T2 over T1 to find this. So the denominator will be 1 minus a half. And in order to find the sum to infinity, I need to plug this all into my calculator. So it will be 64 over 1 minus a half. So the sum to infinity for the area of all of these squares added together is 128 centimeters squared. Great, everyone. I hope today's revision has helped you. I look forward to seeing you again sometime soon.